Hi everyone, welcome to our section 13.4 lecture. Today we're going to be looking at phase changes. I know you read the section on this, but there's a lot of terminology and some stuff that I'd like to explain. So we're going to take a look at that today. So let's begin. So I couldn't find any funny jokes about phase changes or anything, so I decided, what the heck, might as well throw in some psych. They go through funny phases, I guess. So here we go. And I totally agree. Psych is the only show on television that combines pure awesomeness with total freaking awesomeness. So there we go. For all my Psych fans, there's your plug. Alright, now to the real work. So, phase changes that require energy. So these are what you have to input some energy to get to happen. So if you think of something like boiling water, you have to put it over a flame to have it boil if you're using room temperature water. So that's inputting energy to get it from going to a liquid to the gas that you see coming off the water when it starts to boil. This is what we call vaporization, is when we're going from a liquid to a gas. So going in this direction, just like the arrow, from a liquid to a gas requires input of energy to get it to change states. So these are the three states we have: liquid, gas, solid. Now, another one where we need to put energy in sometimes is fusion, which is melting. So when you put energy in, let's say you want to melt an ice cube, you're putting energy in. Is your, if you put it in your hand, it warms it up and causes it to melt. Some other things we can have: sublimation. That's when something goes from a solid to a gas. One of the things that we know of that sublimes is actually dry ice. So that is solid carbon dioxide, and it spontaneously turns into a gas. So you don't see carbon dioxide liquid when you have dry ice. When it melts, it doesn't really melt, it sublimes and it goes straight to the gas form. Now we have the reverse of these, which are a couple more states. So deposition is actually the reverse of sublimation. It's when you spontaneously go from a gas to a solid and you're skipping the liquid phase. We have condensation, which is when we're going from a gas to a liquid. So this is what explains why when you have a glass sitting on the counter, you get, if it's cold inside the glass, you get water condensing on the outside of outside of the glass. That was actually water from the air that condensed on the cold glass into a liquid. So that's where that water is actually coming from. It's not coming from inside the glass. And then we have freezing, which is when we go from a liquid to a solid. Now, freezing is not when we make something cold necessarily. It is only when we're going from a liquid state to a solid state. Same thing for boiling. That's when we're going from a liquid to a gas. It's not when it gets super hot or anything, because it can boil. A substance can boil, like liquid nitrogen boils at a very low temperature, but it's not hot. So it is just when something is going from a liquid to a gas that it boils, or a liquid to a solid, that we call freezing. Let's take a look at our next. Here we have vapor pressure. So vaporization is a process by which liquid changes to a gas or vapor from a liquid. So we have evaporation, which happens only at the surface of a liquid. And we can have something evaporate even if it's not hot. So you think of if you leave a glass of water out on the counter. You're not boiling it, but eventually it will evaporate. So eventually molecules get up enough energy, whether or not you heat it, they will turn into the gas state and evaporate. That's for an open container. Now if we have a closed container, what happens is eventually these molecules out here will reach equilibrium with this pressure and they'll be equal. So we say evaporation, which has reached equilibrium with the liquid surface, is said to have reached saturation. Now this only happens in a closed container, because obviously if we had an open container, we're not going to be building up any pressure in the container because we're not keeping any of the molecules in. So that's what our vapor pressure is. The pressure, vapor pressure, the definition of that from your book is, ooh, that's big, is stated as the pressure exerted by a vapor over a liquid. So this is the pressure that these molecules right here are exerting. So pretty simple definition, works in a closed container. Here's another way to look at phase changes and how the energy input goes. If we want to turn something from a solid to a liquid, in which we would be melting it, we have to add energy. Same thing goes for evaporation. If you want to go from a liquid to a gas, you have to add energy. So melting and evaporation, we're adding energy to change that state. Now the opposite, if we want to go from a gas to a water state, like in condensation, we would be removing energy from the system. Same thing with water and freezing. If we're going from liquid water to ice, we're actually removing energy. So these are important concepts to make sure that you understand. So here we have what is called a phase diagram. Sorry. There's a couple important parts on a phase diagram that you need to know. This one is actually a phase diagram of water. So we have our H2O, and phase diagrams are specific to whatever the substance is. So I'll show you another one in a minute that actually looks different because it's for carbon dioxide. But one of the important parts is called the triple point. So this point right here, where the lines between solid, liquid, and gas all come together, that's called the critical point, or sorry, the triple point, and all three phases can coexist at this point. So right at this pressure and temperature, so right here, at this temperature and pressure, so here is temperature increasing, pressure increasing. Right at this pressure and temperature is where we'll have solid, liquid, and gas all at the same time. Now, what these phase diagrams tell you is at what pressure and what gas a substance is at, it'll tell you the phase that it's going to be in. So for this, if I have a temperature that's, over here on the scale and a pressure that's over here, if I intersected those lines, they're in the liquid section. So at this pressure and this temperature, water would be a liquid. Now if we had one over here and over here, we would actually have water as a solid. And that makes sense, right? Medium to high pressure and a low temperature, that would give us solid water. Along these lines that you see, so I'll circle these. Along these lines here, these are when you have equilibrium and you have both, in this case, between the solid and liquid, this is where it's melting and freezing. So we have substance in equilibrium melting and freezing. Along this line right here is actually where we have sublimation, so going from a solid to a gas and deposition happening. So that's low temperature, low pressure. And then along this line, what we have is vaporization and condensation at equilibrium. So exactly on these lines, those are the phase changes that are occurring. So between a liquid and a gas, that's where we get the vaporization and condensation. Well, the last thing I want to point out on this chart is what we call the critical point. So the critical point is the critical temperature and pressure at which water, in this case, cannot exist as a liquid. So that it doesn't matter how high the pressure goes, I will not be able to get it to liquefy. So that's this point right here. And once again, that's the point at which no combination of pressure will make water liquefy. So important parts on the graphs, make sure you know what the lines mean between the different phases, and also the critical point and the triple point. Now here's a phase diagram for carbon dioxide. I'm not going to go through it in as much detail, but usually the graphs will have a line on them right here somewhere that will be denoted as 1 atm. That way you get kind of a feel for where the pressure is. So 1 atm standard pressure. Now if we look, if we have negative 78 degrees and let's say half an atm, we would have a gas for carbon dioxide. Now if we keep that temperature and we increase it to say 2 atm, now we have solid carbon dioxide. And that's why we have dry ice. It's because it has a lot of play between the gas and solid phases here. Now if we wanted to make it liquefy, we would have to have a high temperature, well, higher. You would notice 31 degrees Celsius is the highest this goes, so it doesn't have to be very high at all. But we need to have a high pressure. So if we have a temperature over here, somewhere, let's say around room temperature, to get it to liquefy, we'd have to have probably 3 atms of pressure just to barely get it in there. So it takes a lot higher pressure. Here's another phase diagram, and this one you'll see quite a bit. It's really important. And this one's not looking at temperature versus pressure. This is looking at the heat that you've added versus the temperature. So we have temperature in degrees Celsius and the heat added. So this one is for, we'll say water. Now, what you need to be aware of is that for the plateaus, we're putting in energy, but the phase isn't changing. So, or sorry, the temperature is not changing. It's because all that energy that we're putting in here and here, it's not increasing the temperature because we're actually taking that energy to break the hydrogen bonds. So we're breaking hydrogen bonds in the case of water. And that causes that plateau. At these plateaus, this is also the point where you have a solid and a liquid, so melting and freezing are going on at the same time. If we're going this direction up the scale, we're going from a solid to our liquid, we're actually melting. And that makes sense, right? You go from solid ice to liquid, we call that melting. Now if we were going from a liquid to a solid, so we were freezing. And when we go this direction, it tells us we're actually freezing. Now up here is when we have both condensation and vaporization going on. Once again, we're breaking those hydrogen bonds. We're giving the molecules enough energy to break the surface of the liquid and turn into a gas. So here we have our gas. And yes, for those that are asking, there would be a plasma state somewhere up here, but we're not gonna worry about that because we can't get to plasma in a classroom. But at this point, you have both a liquid and a gas. So things to remember on this is you can go both directions. Up this chart, we can go this way, increasing temperature. We could be going from a solid down here, so this slanted part is when it's a solid, to a liquid, that's this slanted part, to a gas. And that is an increase in temperature, so as we add more heat, the temperature is rising when it's all in that phase. Once we get to a point where it's starting to move into the next phase, we have a combination of the two. So here at the plateau, we have liquids and a gas. So if I asked you, normally there would be temperatures here, here, here. If I asked you at what point it became a solid, you can look at this temperature, and where it plateaus, that would be the corresponding temperature. So let's say this one was 10 degrees Celsius. That's where this would start to freeze. That would be the freezing point. And whatever temperature it was here, that would be the melting, the vaporization or the boiling point of the liquid. Alright, so a little warm up here. Not a warm up. Well, just looking at another phase diagram. So it asks, what's the freezing point of this substance? Well, when we take a look at it, freezing point is going to be where this first plateau is. So that's actually going to be our 5 degrees Celsius. Now, what is the boiling point of the substance? It's going to be our second plateau. So that looks like it's 15 degrees. Now, what is the melting point of the substance? So melting is when we're going from our liquid state to our solid state. So that's actually going to happen at the same time, at the same temperature as our freezing point. Because remember, here we have both melting and freezing depending on the direction you're going. So let's see, what letter represents the range where a solid is being warmed? So we have A. Since this is a solid, and as we input energy, the temperature is going up. So we're going to say part A. What letter represents the range where the liquid is being warmed? Here's our liquid, and that range is going to be C. And what represents the range where the vapor is being warmed? Well, here we have our gas phase, so that would be E. What letter represents the melting of a solid? So once again, it's going to be happening here at B. That's our melting and our freezing. What represents vaporization of the liquid? It's going to be our D right there, because that's where we're going to have our liquid and our solid, liquid and our gas phases. What letter shows a change in potential energy? So we actually have B and D, because you're storing up energy, you're adding energy, but nothing's happening with it. Temperature's not increasing, so we're just calling that potential energy. Kinetic energy, that's when it's actually sloping. So we have sections A, C, and E have kinetic energy. So things are moving, molecules are moving, temperature's increasing. what letter represents condensation? So condensation is when we go from a gas to a liquid, so that's going to be D, and crystallization happens when we're going from a liquid to a solid, so that would be B. So I know this was a little long-winded, but there's a lot of terminology in this section, and it's really important to understand kind of the phase diagrams, because we'll be using them more as we go along. So make sure that you take the quiz that follows this on the site, and if you can't, make sure you come get a hard copy from me before Wednesday. So this is due Wednesday. Anyways, let me know if you have any questions, and otherwise I will see you in class.